Good afternoon, all. I'm Bhavaneesh Athikary, and I represent Hexagon's Manufacturing Intelligence Division. So today's talk is about the emergence of AI and ML in product development or sustainable product development. So let me start with who we are. So Hexagon is a global leader in sensor software and autonomous technologies. So we're leaders in the design and manufacture space. So around 95% of vehicles manufactured, 90% of aircrafts manufactured, and 85% of smartphones made are touched by our technologies. But our core competency is in connecting the different stages of manufacturing, like design and engineering, production, manufacturing, and inspection through metrology devices. So our portfolio under Manufacturing Intelligence Division consists of design and engineering, which is mainly into the simulation softwares where performance is evaluated in the virtual world. That's from the concept design stage to the final stage of the design. Post that, we have production softwares like CAD, CAM softwares, and also manufacturing process optimization tools. And finally, to inspect the quality, obviously the metrology part, mainly on the hardware side. So in today's talk, I'll touch upon the AI ML's emergence in each of these domains. So let me start with the simulation part. So we all know how the simulation or CAE simulation has impacted the product development. It has been here for more than 50 years now. But there was a lot of talk for the last decade about front-ending simulation, right? So if you see this image out there, what it says is at the initial concept design stage, your cost committed is high, but the information what you have about the product, what you're developing is minimum. And the flexibility to change is high, which goes up as the time goes by. But the challenge is, where do you get this information to take informed decision at the concept design stage? That's where simulation has played a big role, and there was a lot of talk about front-ending simulation. So this chart mainly talks about that. But now, moving on to the world of Industry 4.0 and digital twins, there's always some limitation of simulation to scaling up to the manufacturing side or the digital twin side. Like it takes too long, too much of time for CAE results to come out. CAE data is not available, or too much of data is available to make sense of it. And also a limited number of predictive adaptive models available in the market. So the expectation is that simulation now is powering the design phase. But what about the predictive digital twins? How simulation can help? With time as a constraint, that is where a lot of focus is, and that's where AI and ML is playing a big role. So if our technology positioning is mainly with the product called Odyssey. Odyssey is a solution establishing link between traditional CAE system modeling and machine learning algorithms. So how it tries to reduce the time taken or real-time simulation is through using AI models in your conventional CAE approach. If you look at the conventional CAE approach, the process is more like you have a design, you model it, that's pre-processing part, then the run happens, which is the numerical calculations are solved, that's PDEs are solved, and you have results which are then optimized for the performance what you look for. But these kind of iterations takes a lot of time. That's where these AI models can help you to reduce a lot of time in a very big way, which you will see in the coming examples. So Let me start with some use cases here. So this is an example of a frontal impact where airbag is designed. So this is an explicit solution which takes a lot of time, as most of you might be aware. So this usually takes almost, this example here takes almost 1 hour time, and the example, the animation on the left, what you're seeing is from a finite element solver, which takes almost an hour to solve. And whereas on the right, what you're seeing is the outcome of the Odyssey, which is AI/ML product of ours. So here it just takes 3 seconds, 4 seconds to solve such a run. But yeah, there is a catch here. It's not, it doesn't work on its own. You need to train it. So there are a few number of jobs which you need to run to train that. But even then, if you see the accuracy, even with the animation or with the key parameters what you're tracking, it's so close to 90% accuracy, which most of us will be okay to do with when you want real-time data. There are much more examples. Here, this is another example of an electric vehicle, battery short circuit analysis, where because of the impact, the battery short circuit happens, and we want to see what's the deformation in the battery cell, and also the voltage variation, along with what's happening to the overall structure from a temperature point of view, the temperature distribution. This is a multi-physics problem which takes a lot of time. So here we applied the same concept. And if you see the accuracy of the result, it's almost 98% match in terms of deformation, in terms of voltage, and also the temperature distribution, what you're seeing here. So you can see the plots here of deformation and temperature distribution and the voltage. They are almost an exact match with 98% correlation. With that sort of correlation, and time taken is 2% of the actual finite element analysis. Yes, again, you need to run a few jobs to train your AI model, which is much lesser when you compare it with the DOE-based approach which the industry follows today. One more example of computational fluid dynamics case where a front bumper shape optimization is done, where the objective is to minimize the pressure at a particular point in a front bumper. At the same time, the lift coefficient is the constraint here, and it's been kept as a constraint for this optimization problem. This can also be extended to your manufacturing process simulation, like stamping, welding, where these kind of AI models can work in the background to help people who are not aware hands-on with such simulation works. People on the floor can use this sort of models to quickly optimize what should be the stamping force and welding directions, path, also the clamping locations. Such optimizations can be worked around with the minimum time. Another important area of AI/ML is in the material development, material exploration. There's a lot of focus these days on either from the weight reduction point of view or from a performance point of view. Even the adoption is increasing of non-metals today, where we don't have a lot of properties of these materials. Exploration is one part, and having material properties for different conditions and different tests. So the case here is where you have some amount of tests being done on some of these materials, where the AI model can help you develop the outputs for the rest of the test using the database what you have. Okay, also in the development of autonomous vehicles, we have moved from the physical test to simulations in a big way, where 1 billion kilometers can be simulated in a week's time in simulation, and various scenarios can be simulated. But when you talk about various simulations, various scenarios for an autonomous vehicle, it can be an infinite situation where the programs like this can help you pick the edge cases and simulate around it. So here in this case, it is a fusion of visual sensors which was performed. Another important aspect of this tool is to help you with prediction using images. What you're seeing here is a set of, or a database of tire thread patterns. So you have sound spectrum analysis done, and you have that spectrum for a database of thread patterns. So when you want to analyze for a new thread pattern, you don't have to run a numerical simulation. These kind of AI models can be used to predict, and the accuracy level is above 90%. So it's very good tool to start with and then fine tune on what's could be the best design in the initial phase of your design. This is another example of learning from the images where a tire wheel rim impact analysis is performed on 22 odd different designs, where the number of spokes and the impact velocities are the two variables here. With this database, you can predict, you can see the curves over there. It is almost matching with 90% correlation on what is been predicted using these AI models. Okay, that was more on the simulation side, and also on the smart inspection point of view. We have tools which can help you to detect all the anomalies within your designs, defects. If the tolerance are fine, these kind of checks can be visually performed, automatically performed using these kind of programs. So the image from the camera can be studied, and it needs to be trained, and then it would identify if there is any issue with the quality of the product. Some more examples. This here, what you're doing is you're initially trained to detect any presence and absence of any parts or misplacement of any parts within the vehicle. So it scans through your vehicle and it can tell you, okay, this part has a defect, or this is misplaced, or this is missing. So that sort of work can be done using such a. Also, some more cases where the wrinkles and ripples within or scratches in your subsystem or vehicle can be visually analyzed for detecting these kind of issues. So finally, as I said in the beginning, our core competency is on connecting these three important verticals of manufacturing life cycle, that is design and validation, manufacturing, and quality through a digital thread. And that's how we make it learn continuously and improve the productivity and quality. So how a design twin and a manufactured twin and a lifetime twin, all three are connected through a digital thread of AI-powered real-time data flow threads. So this is a brief of what I could talk on AI ML's application areas. If you are interested in any of this to discuss in depth or in detail, I'll be around. I'll be happy to discuss with you on these topics. Thank you all.